Hello guys, in this chapter we will learn basics math. While we learn it, cause most algorithms are based on it. Math may help you learn the algorithms better, and linear algebra and probability theory are specifically important. Okay, let's get a quick start.
To avoid obesity and improve employees' health, the Big Data Department organized a monthly running activity at the beginning of the 2018s. The rules was as follows. The department set the monthly target for participants at the beginning of the month, and the participants who fulfilled the targets will be rewarded, while those who failed will be punished. The calculation rules reward and punished amount was as follows. And in monthly target and the total reward, the plaintiff's amount receiving equality, and the WI is the total reward and plaintiff's amount in the month I. SI is the total miles each, and DI is the monthly target, and ASI is the difference between the actual distance and the monthly target, and the XI is the reward or penalties amount of each kilometers every month. In the preceding case, what is the reward penalty amount set by the Big Data Department for each kilometer in each month? The coordinates are as follows using the given data. You will build this equations to solve the x is which is the x2 and x3, and calculate one by one. And in this way, the solution of the equations are the answers to the questions. But how we use the linear algebra to solve these problems? And let's see. First, we learned the vector and the matrix. This is a data container. And vector is the array numbers, and the numbers are arranged in the order. We usually call them numbers elements. If we want to represent one element in the vectors, we need to use the index of the origins. And in the two-dimensional space, a vector is the xy, maybe it's the sy, and this is the one columns vector. It's the values in the vectors. The matrix is numerical table of m rows and n columns. It's also m rows and columns, and it will include m rows and n columns, and n, 2, 3, and n and the columns. For the rows, it will 1, 2, 3, and if the number is the AYY, it means that its location in the first columns, in the first rows. If the A2Y, it means that in the second rows and in the first columns. That is the index. There are many types to present a matrix, just like the formula rules. That's how to represent this is the matrix. All symbols between the equal presents are muted in a matrix. This page we will learn the determinant. Maybe it's similar to matrix, but we should pay attention to it. Both the sides of the matrix are the parentheses, and both sides of the determinant are straight lines. And the determinant is usually represented as the DETA. It's a matrix determinant. And there are two signals. The first one is the matrix is combination of the vector, but determinant is a value. Its value is about the area of the matrix. And you can get it by the multi or the eigenvalues of matrix. And the second one, the values means how much multiplication an n-dimensional matrix expands from an n-dimensional addition matrix. For example, matrix 1, 0, 0, 1 its determinant is the 1. If the determinant can write by that, it will equal to 1. And that is the two-dimensional standard matrix, and matrix 2, 0, 0, 1, and its determinant is 2, 0, 0, 1, and it will equal to 1. In two-dimensional space, we all know the rectangular, its area is the 2, so it expands the 2 times from the 1. If we want to get the value of the determinant, we should to calculate these numbers. First, we should calculate this the A11 and A22, and multiply the 1 by the 1, and add the 1 to length and these lines, and also multiply the A minus 1. Also with this line we calculate, and also add these lines and 2 minus the these lines. These are different directions, and I used these lines, the 2 right lines, and multiply each line the elements, and multiply the 1 by 1, and then minus the next lines. So that's like that we can calculate the determinant. Here let's see the matrix operations. When you know the matrix addition, first you should make sure the two matrices is the same size, so as the same rows and have the same columns, and the number of the elements are the same. And you should add their vectors to 1 to 1 correspondings. For example, mutate A is plus B will be used the same index to add. And when you do the scalar matrix mutate, you also can use the key multiplies all elements in the matrix. If you want to do a matrix multiplication, you should make sure that the matrix is the number of the columns is equal to matrix B, the number of the rows, so they can do the multiplications as like that. You should use the first row's elements in matrix A to multiply the first column's elements in matrix B, and then use the second rows to multiply the second columns, and that formula shows the process of their multiplications. For matrix transposition, it is to exchange the matrix rows to its columns and exchange its columns to its rows. That's something like that. And it has maybe it has the 2 columns and 3 rows, and we will change it into the 2 rows and have 3 columns, and there's elements, and just to exchange their operation. And there's the natural transposition matrix, and its transpositions and its transpositions will be equal to itself. And lambda multiplies the z transposition will be to lambda minus multiple and its transposition. Also, they can split and then do the transposition. And also we note that we will note that A multiplied B, the result transposition also equal to B transposition multiplied A transposition. So we change their mutated order. The operation need to add all the diagonal matrix elements. There are 3 rows on the list. First, the trace operation on matrix A will equal to the trace operation on the transport A, and the 2 is transport to operation on matrix A will equal to A. 3. If the A multiplies B and then multiplies the C, they do the transfer operator and get a value, and the value will be equal to the C multiplies the A and to multiplies the. It doesn't matter their orders change and their position change. They you can do the transfer operation and get the same values. That's the nature of the transfer operator. Here is the result of the case, and we can use the linear algebra to solve it. If we know the A, and to build this matrix and build the B matrix, and then we can do some operations like that. If A can be, then this is the two canvas. This just shows the linear algebra operations. Here is the education for the previous examples, and first we should transfer the numbers into the matrix, and this is our parameters, and also after our variables, and we can equal to length parameter. We can use the A to in this present the matrix, and use the X to present this vector, and use C also to represent the line one columns vector. We can easily to calculate the matrix with the one columns and its values x1, x2, x3. So it's easy to solve these problems by the linear algebra. And next we should learn some special matrix. First, let's learn identity matrix and inverse matrix. Identity matrix is simple. All under only a diagnosed element is 1. That's the other elements and is 0. So we can learn the by that it's 1. So we simply that it can be as the 1, 1, 1, 1, 1, and this 0, 0, 0 is the identity matrix. And matrix inverse means that if the matrix to multiply its inverse will be equal to identified identity matrix. That will call the matrix A. It has the matrix inverse, and the matrix inverse A is denoted as the A minus 1. Let's see something about the diagonal matrix. All the diagonal elements are not zero. They can have different values. Maybe they can value they can be the 0, can be 1, and the other elements will be 0. It's like that. We can simply write that, and in the diagonal lines, it can different numbers lambda 1, lambda 2, and lambda n, and other lines will be equal as the diagonal matrix. And it follows these rules, and the sum, difference, products, and square powers of the elements on the diagonal matrix are the sum, difference, product, and square power of elements along the main diagonal. And the inverse of the diagonal matrix is to inverse every diagonal element. That's very easy to understand. Let's talk about symmetric matrix. If the matrix is equal to its transposition matrix, it is a symmetric matrix. If the transposition matrix is equal to its inverse matrix, and the matrix is called to orthogonal matrix, so the transposition matrix multi itself is equal to 1. Next, let's learn Eigen decomposition. Eigen decomposition is widely used in matrix computing because it can largely cut our data size and easy to calculate our data. And this is because some property of matrix is not obvious. We can find them through the Eigen decomposition. Here the formula like that. We can present the matrix A like that. Use its Eigen and Eigen vectors. And here is the formula. If the matrix A multiplies the vector lambda and equal consistence the lambda mutate the alpha. The alpha is the eigenvector of the A, and lambda is the eigenvalue of the A. And for example, because the A multiples the alpha is equal to 2 multiplies the alpha, and the alpha is the eigenvector and 2 is the eigenvalues. Here we will learn how to calculate the eigenvector and eigenvalues. According to the formulas, A multiplies the alpha and equal to the lambda equal to the alpha, and then we should to A alpha and then minus the lambda alpha is equal to 0, and we can also write that A minus the alpha interested in identity matrix and to multiply the alpha and also equal to 0, and then we can use the A's matrix multiplies the diagonals matrix. Diagonals they have the lambda. We can calculate the determinant and equal to, and then we will use to calculate the lambda is. And if we know the lambda, then we get the to alpha, and to calculate the alpha, what's the alpha is. And here is examples, and let's finish it together. Here we can get the aging equations, and this to get the matrix, and the matrix is matters the lambda alpha. It can you write about that. So the eigenvalues of the A, the lambda 1 can be the 2, also can be the 4. Let's think the lambda 1 equal to 2 in this case, and the current eigen specifies this and 1 by 9. So we can find that the x1 is equal to the x2. So when the lambda with its eigenvalue is equal to this, and eigenvector will be as this one, the P1. And if the lambda 2 is equal to 4, and we will find that that's x1 equal to the minus the x2. So the eigenvector is like that, and we can calculate with different numbers because there is simply vectors, and we can calculate any numbers to key, and the key it doesn't equal to 0. It can both satisfy these settings. So that's the process of how to calculate the eigenvector and eigenvalues. For symmetric matrix, its eigendeterminant has a special situation. Is giving the decompositions like this formula. Here some definition of the matrix accuracy. A matrix whose eigenvalues are all positive is called positive defined. And if all the eigenvalues are negative, then it is negative defined. A matrix whose eigenvalues are all positive or 0 values is called positive semi-definite. And if all eigenvalues are negative or 0 values is negative, the semi is defined. Here's the singular value decomposition. It means that the matrix is decomposed into the singular vector and the singular values, and it's a formula like that. We can use the very 3 vectors to represent A. The matrix U and V are both defined to be orthogonal matrix. The columns of U are known as the left singular vector. The columns of V are known as the right singular vectors. The matrix D is defined to be the diagonal matrix. Note that D is not necessarily square, and the elements on the diagonal line of D is referred to as the singular values of matrix. Here, let's learn the more Pinzo's pseudo-inverse. It is useful in solving linear equations. It is defined as these formulas. We often use the formula to calculate the pseudo inverse, and the UDV are the singular vector demonstrated we talked about before, and it's very useful. Okay, let's introduce a useful argument, and it's called pre-simple component analysis. Pre-simple components analysis, it is the set of the linear unrelated variables, and we do orthogonal transforms on the group of variables, and the variables that may have the core relationships, and then we get the pre-simple components. It uses the field related orthogonal variables to replace the all original variables, and we also save most information of the original matrix. Let's see an example. If there are n objects and each object is composed x1 is xp, and just like the table shows, after the PCA, and we may use the x1, x2, and to replace the x1 and to extra p to use these vectors. We used this method to save most information about the data and to decrease and to cut the data size. That makes factors and their pre-simple components, they have no relationships, and they are all independent. And the original variables are the vector x1, xp after dimensional reduce processing and set the compare index. And these days the new variables are the z1 from zm, and this called the first and the second and m's main principles of the x1 and xp. We have the following expressions like that, and that. To obey the m pre-simple components, the steps as follows. And first, we can put the coefficient Lig and meets the following rules. And Zi is not related to Zg, and Z1 has the largest variance among all the linear components of the x through s this vector, and Z2 has the largest variance among all the components of the x1 to the xp. So according to the above values, Lg is also the engaging vector of the m largest values of the coefficient matrix corresponding to x1 to the xp. Is the cumulative contribution rate of the first i's main components reached 85% to 90%. Those components are used as the new variables, and that's also to calculate the pre-simple components. If you want to learn more, you can to learn some blogs or books and for some details. And now we don't to explain these formulas.
Now we have learned some basics knowledge about matrix and some special matrix and Eigen decompositions. In next video, we will learn the probability theory and the information theory. See you in next video. Bye.